myself the chance to present some of our recent work. I will try to be entertaining and show you new simulations of vortex matter in multiband superconductors. And you all know about vortices, and we have been studying vortex matter for over 20 years numerically. Plethora of wonderful results particularly in single band superconductors and under mesoscopic confinement. What is important is that vortices are beautiful objects, but also they are sometimes smoking guns for underlying new physical phenomena. And some of them were mentioned this morning regarding types of superconductivity, where clearly you can see different behavior of vortices in different materials. Now, especially in recent years, since the discovery of two-gap superconductivity in MgV2, but in recent years with peptides, we want to know about vortices in multiband or multi-gap superconductors, and type 1.5 was mentioned in that respect. Again, is very unusual vortex behavior, which now we understand under the picture of this critical type of superconductivity between type 1 and type 2, which is quite generic, I would say, for single band and multiband superconductors, but more pronounced in multiband superconductors. Now, what I want to talk about today is an extension of this, so the vortex behavior is not captured by this picture, and in particular the fractional vortex states. So these are the vortices that carry fractional amounts of flux, fractions of flux quanta. And in particular, they can appear due to the competition of multiple length scales in the problem, but they can also appear due to phase frustration, which was mentioned by Lara, between the band condensates, and neither of these cases is actually captured by this simple picture. So actually, there's much more to do. We are far from final answer. So I will start from the multiple length scales, and probably I will not have time to go to this problem, but yeah, let's see how far I can get. So for pedagogic purposes, I will just use two-component Ginzburg-Landau model for a two-gap superconductor. We have the energy functional, which is basically given by the single gap contributions from the two condensates, the Josephson-like coupling between them, and of course they are screening the magnetic field together, so there is magnetic field, magnetic coupling between the condensates. Now, temperature enters the calculation through these phenomenological constants. Of course, they can be derived from microscopic theory. I'll come back to that a bit later. But this is the simplest model we can have. And by minimizing the functional with respect to psi1 and psi2 and the micropotential, you have three equations for describing which you have to solve self-consistently to obtain the behavior of the system in applied magnetic field. These are some, this is written in dimensionless form, so these are the scaling parameters that I'm using. Now, first, I want to point out that this is, we often call this Josephson coupling, but of course it's not Josephson. It looks like Josephson, but it's not. And you can see that from the contribution of the coupling in these two equations, you have psi1 coupled to psi2 here, and psi2 coupled to psi1 here. And both coupling constants, both contributions are negative. So that means that if you increase coupling, you are enhancing both psi1 and psi2, which is different from the regular Josephson effect. So, and the second thing that I want to point out is that this coupling always tries to match the spatial profiles of psi1 and psi2. What does this mean? Well, if I have minimum in psi1, ideally it wants to attract the minimum in psi2 as well. In other words, vortices in different band condensates attract. Okay. So, in principle, we shouldn't have fractional vortices independent from each other. In bulk, they should sit on top of each other and behave as a composite vortex line, okay, carrying the flux line. However, if we put boundary now on our superconductor, let's imagine we have a mesoscopic superconductor. Because of difference in length scales between the two condensates, there will be difference in confinement acting on the two condensates. So you can have a situation that you have different number of vortices in two coupled band condensates, and I showed here just one example for very weak coupling between the bands of different number of vortices in two condensates. Ones are given in blue, the others in purple, and you can see that the numbers don't match. And of course, you also have asymmetric, clearly asymmetric vortex states, which in principle could be observed by standard experimental techniques. If we had a material with very weak coupling between the band condensates, okay, which is not clear that we do. So yeah, as I said, you can even have a situation that you have one vortex in one band condensate and no vortices in the other, and this would be a typical magnetic response of such a state. So asymmetric and clear to see. Fine. Now, what does this mean? Well, basically, it means that you have one weak condensate. If you imagine, if you have one weak condensate and one strong condensate, which was mentioned in a couple of talks this morning, and you have weak coupling between them, so your field temperature phase boundary for different vortex states, which are regularly measured by transport measurements, should have some distinct mushroom-like behavior, where this is basically the critical field of your weaker condensate. And these fractional vortex states should appear here at these low temperatures. Okay. Now, this is, if you measure the magnetic response, now this is the calculation of the magnetic response, you will see by increasing magnetic field, which is standard magnetometry procedure, you will see jumps which correspond, if you follow the gray line, sometimes correspond to the integer of flux quantum, sometimes to the fraction of the integer. Okay. And of course, it's not 1/2. It can be, but it doesn't have to be. That depends on the balance between the two condensates. Okay, which one is stronger, which temperature we have, and so on and so forth. But as a matter, as a general principle, in mesoscopic multiband superconductors, we can have fractional vortex states. Now, to give a bit of, let's say, caution, because there are many studies of this kind. We did this in 2010. There have been many studies of fractional vortices between then and now. People use Gainsborough-Landau theory without much care for the parameters. So phenomenological parameters are not entirely phenomenological. Well, actually, they are connected through microscopic parameters. They are not independent, so you cannot change psi and lambda of the two condensates at will. That's not a free parameter. You should go to microscopic theory, express your coefficients through the scattering matrix, the Fermi velocities of the bands, and the partial density states, of course, and total density states. And this would be the full form of the Landau theory with those coefficients taken into account. And this is the time dependent variant of two-component equations, where, well, actually it doesn't, it's kind of self-explanatory. I don't have to spend too much time on this. But I want to show you, the reason I introduced this is that I want to show you now the dynamics of fractional vortices. So how fractional vortices behave when we apply current to our superconducting sample. You can already anticipate that the flux flow regime, the phase slip phenomena, everything will look different. If my stationary behavior is different, then dynamic one will also be different. So this is a two-band slab, which we use in the simulations. I give some parameters, some of which are MGB2-like, but it's not my intention at all to simulate MGB2 here. And we typically stay very close to critical temperature because of the validity of the theory. And this is the, okay, it works, I'll wait for a moment. So this is the one band condensate, and this is the other, in the case of very weak coupling between the bands, and 3 times larger Fermi velocity in one condensate compared to the other, which means 3 times larger coherence. So I will play it again. This is a defect here, and you can see that vortex in one condensate feels the presence of the defect, whereas vortices in the other do not care about the defect being 3 times larger. Moreover, you see that they exhibit completely different dynamics, but at the end, they sit in the same positions. So in the stationary case, they sit on top of each other. Dynamics very different. So not only the dynamics is very different, but now vortices in two-band condensates are selectively sensitive to the imperfections in the system, including ping. So if I do another set of simulations at different magnetic fields, you have similar behavior, but now if you put more vortices coming in at larger magnetic field, you will see the behavior which is completely different. And the end result is also different. Here we have giant vortices, and here we had separate vortices. So if I now apply current to this last seen state, you see behavior that is completely off the charts. So this is, we can call it flux flow, but there is no periodicity in it. This is voltage as a function of time for this case, and the Fourier transform of it. They behave, these two band condensates behave completely differently. And if we increase the coupling, then these vortices will sit on top of each other. That's shown here, and you get perfectly periodic signal of voltage as a function of time. So now the fundamental question arises, are these fractional vortices independent of each other? So they look very independent. They have completely different dynamics, different sensitivity to the defects and the boundaries, but are they really independent? This was addressed in PRL 2 years ago and followed up PRB by Milosevic and Reichert. They studied this using molecular dynamics simulations, and they assumed simply that you have regular vortex-vortex interaction within each band condensate, and also the interaction between fractional vortices between the bands. Okay? So this is attractive, so vortices between bands, they attract, and they repel within the given band. Okay? So this is supposed to be a pure type 2 case, without going into other types. Okay, so what they get is, if they apply current to the system, if they take different size of the vortex cores, if they take different Fermi velocity for the two parts of the vortex, the current will have different action on two parts of the vortex, and they will split at some finite distance. But if this difference in the Lorentz force is larger than the coupling between these two parts of the vortex, then you can completely dissociate fractional vortices, and they can move completely independently from each other, giving separate voltage signals, and so on and so forth. This was the main message of this PRL paper. In order to check this, we took two-component Inverlando theory, and we put the non-composite vortex ansatz. So we basically introduce part of the fraction of the vortex in one condensate, fraction of the vortex in the other. We fix them at distance, in this case, 20 units in epsilon 0, right here and here, with some coupling. And then you see that, of course, the vortex in one condensate creates depletion in the other condensate, and vice versa. This is what you get when you relax the amplitudes for fixed vortices at this distance. But what is more important is that when you separate them, going from zero separation to going to infinity, the energy diverges. Okay? And this is purely parabolic interaction. Why is this important? Well, it does not saturate at large distances. It does not go to zero at large distances, as presumed by Wien and Milosevic in their model. Therefore, no matter, even if there is difference in the Lorentz force acting on two fractions of the vortex, you can never overcome this attraction between fractions of the vortex in a multiband. What does this mean? Well, actually, here between the bands, you should plot now the phase difference, and you will see the phase solitron. So this is now the complex plane for describing the phase difference between the bands. So between these two vortices, they will be connected by the whirl of the phase difference between psi1 and psi2. So this is, if you want a real picture, this is like two pancake vortices connected with the Brozosian string. Okay? But now we are in K-space, so we have two fractions of the vortex connected with this phase solitron. So if we now take full-blown numerical simulations, these are the parameters we take. Again, it's not really crucial which parameters they are, but I plot here I multiply psi1, the densities of psi1 and psi2, and I take two vortices to be two fractions, a little bit different from each other. So one thermal velocity is just 50% larger than the other. Now you see that larger vortex enters first, and then the smaller part enters later because the barrier is different for them. But then the small one catches up, and they move together until they start feeling the next boundary here. Then, of course, the big one will run away again. But they definitely want to move together. If I take larger difference in Fermi velocities, I create larger difference here at the entry, and you see that I separate these two fractions of the same vortex by a very large distance. And this field of view is 1.8 microns for these parameters. So we can separate them to a very large distance, say half a micron or a micron. But nevertheless, once they are both in, the small one moves much faster, catches up with the big one, and then they move together. So actually, even the premise that the current has different action on two parts of the vortex is wrong, because actually you have, if I go back to the theory, you have diffusion constants multiplying the Fermi velocity squared, and they cancel each other, so the action of the kinetic term in the Landau theory on both fractions will be the same. Okay. So you can separate dynamically fractions of the same vortex, even to very large distances, but in stationary flux flow, if I can say dynamic equilibrium, they will move together with the same velocity. And again, if I even take larger difference in the size of the vortex core, we just increase this effect more and more. So this is like two particles on a spring, the new one comes in, and then one is attracted to the larger fortress. So where is that spring? Well, it's in that phase difference that I showed you. So this is now in color, a little bit better. This is psi1 squared, psi2 squared. And this is the cosine of the phase difference between two condensates. And you see this is first the big one coming in, and then the small, and you will see the phase string. There it is, which plays the role of the spring between the two parts of the vortex. Of course, this string is very energetically costly. That's why it shrinks. Now, to have a simple model for this, you have simply two particles of a string with some simple linear force between the two parts of the vortex, and you can model this is a very simple equation, which of course solution is the exponential decay of the distance between the fractional vortices. And if we compare this to the numerically obtained distance between two parts of the vortex, it really fits extremely well. So we can say that fractional vortices have a sort of behavior like a bag model for quarks. So it's exactly the same. You can stretch, you can separate them, but then there's linear force that puts them back together. So this is confirmed in this calculation. And if you have larger coupling, but not large enough that it's effectively a single band behavior, you will have some modifications to this. Instead of parabolic, you will have parabolic plus quartic term for the interaction between parts of the vortex. But this does not change fundamentally the behavior. You have so-called Duffing equation. There's this nonlinear term here, but still the behavior is the same. So just to, if I didn't convince you yet, I just want to show you this case. I deliberately found the case where I have big part of the vortex which came in. There's no small part. This is the thing. There's another big one, and only then the small comes in and runs straight through this guy and goes back to its original part. So you can see now, if you see now, there will be another big one and another string formed. Takes some time. There it is. But the small one knows exactly where to go. And this information is encoded in the phase, or if you want, it's encoded in the flux quantization, of course. Because we are talking about system out of equilibrium, but nevertheless, in the stationary, in the dynamic equilibrium, we should have satisfaction of the flux quantization. So, the vortex dissociation is not possible. You can split vortex in bulk. You can split vortex far apart for extended periods of time that will give you new behavior, new dynamics, if governing length scales of two bands are sufficiently different. So now the question is, can we have sufficiently different length scales and weak coupling between the condensates? Okay. So, where to find this? Well, this is what we discussed in our paper on hidden criticality. If you have two bands which are two gaps which are decoupled, this is the behavior of the gaps as a function of temperature. If you have them strongly coupled, they follow each other to the same TC. But if you have weakly coupled bands with different TC, you will have this kind of behavior of the weaker gap. Okay? If you translate this to the sizes of the vortex core, you translate this to the healing lengths of the condensates, then in this case, you should see a peak in the size of the vortex core in the weaker condensate, close to what would be TC2 if they were decoupled. Of course, they're always coupled. This is what you expect. So we showed this using Boglevo-Lejeune theory. If you're interested, you can read more here. We simply calculated the size of the vortex core for a chosen set of parameters. Weak coupling going to strong coupling when of course everything is the same in two band condensates. And even if you choose parameters such that at zero temperature you have exactly same healing lengths in two band condensates, close to the critical temperature of the weaker gap, you will have pronounced difference in the size of the vortex core in two condensates, in this case over 3 times. Okay? And I'm counting. Thank you. So that's very nice. We have proven analytically that this is indeed hidden critical point, that if you construct Hinsburg-Landau theory in coupling as the small parameter, you will get behavior of the weaker gap, susceptibility, and the healing lengths which obeys the usual Landau critical exponents. So this is really critical point. But what is really important now is, are there materials that can show this kind of behavior? Well, if I take some of the known two-gap materials and compare their parameters, what is important is that you want to have TC2 significantly far from TC1, so that you can see the effect of hidden criticality, and you want to have weak coupling between the gaps. So MgB2 is not a good candidate. Osmium diboride is pretty good candidate, but has very low critical temperature, which makes it inconvenient. Lithium iron nictide is reasonably good, because you have TC27, TC18, but quite strong coupling still. But then vanadium trisilicon seems to be very good. You have critical, this T star, where you expect hidden criticality of 9 Kelvin and TC of 16.5, very weak coupling. Or chalcogenides, generally speaking, without going into details, again, are a good candidate to observe this behavior. And some of this has been observed in the past. So, for example, the behavior of superfluid density, which is consistent with this picture of two gaps, weaker and the stronger one, and hidden criticality close to this cusp right here. Even estimated parameters fit perfectly in the theory. Then again, iron telluride selenide. This paper, I don't know, probably is published in the meantime, but you see the gap, weaker gap, ceasing at about 9 Kelvin. Again, hidden criticality should appear there. Or vanadium trisilicon. This is the only evidence, experimental evidence I found from a relatively old experiment in Russia, where again everything is consistent with the hidden criticality model. So I would say that close to this temperature and in these materials, you should expect fractional vortices to play a very, very important role. And I clearly don't have time. I just want to mention again that you can also have flux fractionalization in multiband superconductors due to phase frustration between the band condensates. And you can also have them in two-gap superconductors, dirty two-gap superconductors. You can have time reversal symmetry breaking, which is just a month ago shown by Koshilev and Stanev. And I have those simulations as well. For those of you interested, I'll be glad to show you that later. So I'll just leave you with the summary. And thank you for your attention.
Thank you very much. The talk is open for discussion.
So I have a question about, you show the cases when the damping rules of the dynamics is always overdamped. I didn't have much control on how you can change or tune the damping and the elastic constant. Are there possibility for having oscillatory damping, so to see some oscillation in the motion before you go to the equilibrium? To see some oscillation in
I understand what you're asking. I don't think I have a good answer. Of course, we didn't see it, but if you had pinning, I would say definitely yes, because the interaction of the fractions with pinning would be different. And the formation of the core around the pinning sites would also give you mass. Well, it's not mass, but in this context, mass. So I would say in that case, for sure, probably
you could observe some
oscillations of the.
Thank you.
Could you explain to me your statement that the vortices in different bands attract? Because normal intuition is vortices repel.
Yes, these are the full vortices. The vortices we know, they of course repel in type 2, but these are fractions of the same vortex in different band condensates, which are connected by the current, the zero current contour and the flux quantization. And the Josephson coupling term wants to match the profiles of psi1 and psi2. And the magnetic coupling term also wants to put them together and compress all the flux in one point.
And what about the kinetic energy?
But that's included in the current. Right? I don't know if I understand.
But the same argument, just vortices in a single component system. The kinetic energy keeps them far apart.
No, but here you have two components of the current, which you have to sum together. So these are not two superconductors. This is, I can see how this can be misleading, but it's basically.
The J1 squared plus J2 squared, or J1 plus J2 squared?
No, I mean the current is just the sum of the two. So it's just J1 plus J2. I don't know what squared.
No, I think the kinetic energy.
It's just J1 plus J2 squared.
Squared.
Yes. So the current is just the sum of the two. Can I take another question?
Bye-bye.
So you mentioned paper by Lenin and Milosevic, and they wrote this interaction neglecting Josephson linear confinement, but they wrote it under very specific conditions. If I remember, they say it is, they consider Josephson lengths to be much larger than intervortex distance, and they write this approximation only at length scale smaller than Josephson lengths, which is reasonable. If I understood correctly, in your simulations, the Josephson length is much shorter. Did you do simulations which meet the same condition as in Limper? This one question that, if you allow me, just one more question.
Can I quickly answer this one and then, no, just to quickly answer the first one before I forget. You're right. I mean, maybe not all parameters match the exact conditions, but we did check the same conditions as Lin and Bolevsky. The problem with their approximation is that during dynamics, you are going within the limits of the approximation and outside the limits of the approximation. So I would say that they are right to a certain extent, but after that, they get out of their own approximation. If you know, when vortices get too far from each other, then they don't dissociate, but actually the they come back together. And
so if you consider also the relative phase between these composites and come into play, is there a regime where you could have spurions?
Absolutely. Again.
Where would that be?
So in this case, we didn't have them, but if you have, for example, dirty two-band, if you have time reversal symmetry breaking, then definitely you have skyrmion type of solution. Of course, it's a collection of fractional vortices connected by a phase domain wall. So this phase that I showed the string, it just closes up, and that effectively becomes a skyrmion. Of course, it's not the same.
Another one, very short. Very short.
So there were two ingredients in your talk which I have hard time to connect. So you mentioned this phase diagram where you speak about critical region, and at the same time you acknowledge that in two-band superconductor there could be big disparity of the coherence length. So
healing length.
Yeah,
healing length.
Yeah, but also coherence if you not even healing length. So critical coupling is critical because the Bernoulli bound is satisfied. So, and as the only way to satisfy the Bernoulli bound is in multi-component theory is to, when you have different coherence lengths equal. So, how can you
just make a long story short? This diagram is obtained with extended Ginsburg-Landau theory, and by construction is different from the two-component or multi-component model. But this was actually what I asked you an hour ago. These lines you can also define in the two-component Ginsburg-Landau theory, and you will get the same result, at least close to TC. So fundamentally, it's not different. It doesn't really contradict as long as we are in the domain of the validity of the theory, which is close to TC.
Okay, perhaps we have to stop because, okay, thank you very much. And,